this question's fairly simple in the sense that they've already given you all of the concentrations, and you now just need to calculate Kc. Remember, Kc is equal to the concentration of the products raised to the power of the coefficient divided by the concentration of the reactants, multiply them together, raised to the power of the coefficient. Literally just substitute in the values, 3 times 10 to the negative 2, we square that, 0,9 and 1 cubed, and you land up with 1 times 10 to the negative 3. Does this answer indicate a high or a low yield of ammonia? Ammonia is favoring the forward reaction. This number is smaller than 1, so it's going to be a low yield. And what effect would the removal of NH3 have on the equilibrium constant? Remember, the equilibrium constant only changes if there's a change in temperature, so it will have no effect at all. If 2 grams of a sample of ammonium hydrogen sulfide is sealed in 500 centimeters cubed at a temperature of 100 degrees, we've got the following dissociation that takes place. So what you can see is that it breaks up. This is actually a decomposition rather than a dissociation, because it's not ions that are splitting apart. It is actually 2 new compounds that are formed. So it's a decomposition. At equilibrium, it is found that we've got a certain concentration of ammonia, and now it wants me to calculate the Kc value. So let's go with the Rice table. And the ratio is 1:1:1, so that's quite nice and easy. And then to start with, they said to me I had a certain mass, a 2 gram sample. So 2 grams, I'm trying to find the number of moles. Number of moles is equal to mass over molar mass. And the molar mass of ammonium hydrogen sulfide is going to be nitrogen, 14 plus 1 plus 1 plus 1 plus 1 plus 1 plus 32. And it turns out that it's 51. And I'll end up with 0,04. So the starting number of moles is 0,04. Of course, I don't start with any reactant or product. I don't consume any reactant or product. There is a link between the consumed of the reactants and the amount or the number of moles at equilibrium. And now let's see what other information that they give me. At equilibrium, I am told that the concentration of ammonia is, and so 7,28 times 10 to the negative 3. We've got the size of this container. It's 500 centimeters cubed, which means it's 0,5 decimeters cubed. I can now work backwards and say that the number of moles is equal to the concentration times the volume, and I land up with 7,28 times 10 to the negative 3 times by 0,5, and I land up with a number of moles of 0,00364. Now, obviously there's a ratio of 1:1 over here, so I'm going to put that in over here and realize immediately that this number turns out to be exactly the same. And if I think about it, Kc, because this is a solid, Kc is simply equal to the concentration of the products raised to the power of their coefficients, and we're going to leave out the solid. So I've actually got enough information without completing the whole rigmarolious timetable, at least table over here, because with these decimals, it's turning out to be quite an ugly table. So I'm now just going to substitute in these 2 numbers over here up into there, and I find that by multiplying those 2 together, I land up with 5,3 times 10 to the negative 5. I could have carried on with the table. I could have then said it's a 1:1:1 ratio. There I need to go 364. That then turns out to be 3636. It's the same sort of thing. And dividing through, I land up with 7,27 times 10 to the negative 2. But then this piece of information is completely redundant because it's all for a solid anyway. Consider the following hypothetical reaction. We've got A's and B's and making some C's. We are told that initially I'm going to, so let's just rise this up. And we have got 1 is to 2 is to 1. And they start with 5 and 10. They then say to me, they pumped into a 4 decimeter cube container. Good news, it's already in decimeters cubed. I don't need to do the conversion. And C, the concentration at the end is 1,2 times 10, no, sorry, moles per cubic decimeter. So I can work out the equilibrium number of moles. How do I do that? I'm going to say number of moles is equal to concentration times volume. So it's 1,2 times by 4, and I land up with 4,8. Remember, I've got a link between the consumed of the reactants and the equilibrium of the products, and it's 1 is to 2 is to 1, so it's going to be 4,8 over there, 9,6 over there. Then I subtract, and I say 5 minus 0,4, sorry, 4,8, I get 0,2. 10 minus 9,6, I get 0,4. Do the division, number of moles divided by volume, and I land up with 0,05 and 0,1. Kc is equal to concentration of products as long as they're gas or aqueous raised to the power of the coefficient, and we land up with that. You must write this expression down because it's worth a mark, and if you get everything else wrong, at least you can get that 1 mark. And then you're going to go 1,2, 0,05, 0,1, and we square it, and we land up with 2,400. In the process, I've managed to do everything. What's the concentration of A at equilibrium? It's 0,05. Of B, 0,1 moles per cubic decimeter. Don't forget you're going to need units. Equilibrium constant, 2,400. The volume is then reduced to 2 decimeters cubed, while the temperature is kept constant. A new equilibrium concentration of C is found to be 2,44, which is slightly more than twice the original value. You would expect it to be twice the value because I've halved the volume. So, you know, if you went 2 over there, you'd expect that to be 2,4, which it's not. It's 2,44. Why is that? Because I've got 3 gas moles on the left and 1 gas mole on the right. So as I increase the pressure, I'm going to favor the forward reaction, and I am going to actually make a little bit more C in favoring the forward reaction. And then they say if the temperature falls to 400 degrees centigrade, so I've cooled it, what will happen to the concentration of C? Answer by stating increase, decrease, or remain same, and explain your answer. As you know, I always like to explain my answer first because otherwise I don't know what my answer is. So I'm going to start by saying low temperature favors exo. This reaction over here is an endothermic reaction. Delta H is greater than 0. So it's going to favor the reverse, or you would need to say this reaction is endo. Therefore, reverse favored. And therefore, the equilibrium concentration of C would decrease. Remember, the square brackets mean concentration. So I would have less of the product being made.